Good evening, everyone. And thanks for coming out on Halloween to the opening keynote of our symposium, From Lab to Site, Innovation in Concrete. I'm Jonathan Massey. I'm Dean at the A. Alfred Taubman College of Architecture and Urban Planning, and I get, in my figurehead capacity, I get to officially convene this event and welcome you all and hand things off to some of the people who've done the real work of planning and conceptualizing and organizing this, what I think is going to be an incredible day and a half or day plus long event. I'll say a little bit more tomorrow morning when I do the same thing again, but over in the Taubman College Commons to kind of welcome folks to tomorrow's symposium. But basically, there are a few things that I think are super exciting on the docket for tonight and tomorrow, and I just thought I'd signal some of them for those of you who have not had a chance to dig into the program or who maybe have not quite seen it the way I do. But I'm thrilled that we are focusing on concrete in this work that we're doing tonight and tomorrow. Concrete is one of the most used building, it is the most used building material in the world. It has a deep, long history, but it also transforms fast, and it can be an incredibly low-tech material. It can be an incredibly high-tech material, it's also a carbon-intensive and resource-intensive material. So you've probably seen articles about the world running out of sand because of all the construction in concrete, or the questions about the carbon, the greenhouse gases generated by the production of concrete. And all of those together mean that every innovation that a faculty member or an industry partner or a research scientist or an architect makes in using this material, or a student, every innovation in concrete is extra impactful because it has the potential to ripple out through that large volume of construction with significant implications on climate. And so this is a field where even the smallest changes can actually have dramatic significance. So I'm thrilled that we're focusing on concrete for that reason. I'm also thrilled that this is a partnership between the architecture program at Taubman College and the Department of Civil and Environmental Engineering at the College of Engineering. This is a topic that really, to do it justice, we need a multidisciplinary perspective. And the fact that that we are collaborating between these two units, I think, is going to enrich the conversation substantially. It will guarantee that we think about concrete in a much richer range of ways than we might on our own, either as just engineers or just architects. And so I'm very proud of that collaboration, which has grown out of research partnerships between our faculties. And so it's nice to be able to share in a public event some of the collaborative discovery that's happening in labs and research projects. And then finally, I'm really thrilled about tonight's keynote speaker, Mark Burry. You're going to get the real introduction in a moment from Wes McGee, but Mark is a person whose work has been inspiring to me ever since I first heard about the project at the Sagrada Familia that I think will be a major focus of his presentation. And so I'm very happy to meet this figure whose work has been inspiring me from afar, and to go learn about it a little more deeply and see what conversations tomorrow, the presentation tonight, sets up. So I'm going to hand things off to one of the organizers of this event, Associate Professor of Architecture, Wes McGee.
Thanks, Jonathan. So it's certainly my great pleasure to introduce Professor Mark Burry tonight. He's a registered architect and the founding director for the Swinburne University of Technology's Smart Cities Research Institute, which is a position he took up in May of 2017. Mark has published internationally on two main themes: putting theory into practice with regard to procuring challenging architecture, and the life, work, and theories of the architect Antoni Gaudi. He's been senior architect to the Sagrada Familia Basilica Foundation since 1979. His work at Sagrada Familia highlights multiple aspects relevant to tomorrow's symposium, from the link between computational design and construction, to his innovative use of technology, to work on one of the most significant building projects in contemporary history. I first met Mark in 2011, and having seen presentations of this work in a number of academic conferences, I can say that their use of technology has led the discipline in new directions, from the earliest uses of CAD and 3D printing in the design studio to the robotically carved granite columns of the Sagrada Familia facade. And it has clearly inspired a generation of like-minded researchers, including myself. In 2001, Mark founded the Spatial Information Laboratory at RMIT before establishing the Design Research Institute in 2008. He joined the University of Melbourne in 2014 as Professor of Urban Futures at the Faculty of Architecture, Building, and Planning, where he's since helped develop the faculty's capacity to consolidate research in urban futures, drawing together and augmenting expertise in urban visualization, urban analytics, and urban policy. Mark has an extensive list of awards, and I certainly won't touch on all of them, but just a few highlights. In May 2006, he was awarded an Australian Research Council Federation Fellowship, now known as the Laureate Fellowship, which is Australia's most prestigious peer-assessed funding award in acknowledgement of his international leadership in the field of complex architecture and convergent design. And in 2006, he was also the recipient of the Association for Computer-Aided Design and Architecture Annual Award for Innovative Research. In 2018, Mark was appointed an officer to the Order of Australia for distinguished service to spatial information architecture as an academic, researcher, and author, and as an innovator in the applications of digital manufacturing, construction methods. And in the same year, he was elected a Fellow of the Australian Academy of Technology, Engineering, FTSE, which is a rare honor for an architect. So we are thrilled he has joined us tonight to kick off our symposium, From Lab to Site, Innovation in Concrete. Please join me in welcoming Professor Mark Burry.
Thank you, Wes and Jonathan, for the introduction. And I have to thank TN for the communication and Katie Cole for a most extraordinarily well-organized event. I've arrived from Australia and it's been a very simple process. I'm so pleased to be here at last. As you probably know, this institution is world famous for lots of reasons, but not least digital fabrication, and that's been my life for several decades. Not that I ever thought that would be what I was going to do as an architect. We were taught by Bill Mitchell when I was at Cambridge University in the 1970s, and he patiently showed us how to use punch cards to compute representation of a cube, and the climax for this semester was being able to move the cube round on an oscilloscope and get a perspective view of it. And we thought this was a total loser, not Bill, but the activity, and none of us thought computers would have anything to do with us. But history's proved us wrong. I'm going to just quickly put some framework. I'm going to talk about Gaudi tonight. I think the most effective way to get into the topic is to give a review of innovation and making a difference that project has afforded, just as Wes has sort of outlined. But I put a bit of background on the topic of going from the laboratory to site. Sagrada Familia is a living laboratory, and it has been from its foundation. But I'm intrigued by Jonathan's account of the link with civil engineering. I was at Cambridge University, and the civil engineering faculty was 50 meters away from us. We, in 5 years, went there once, I think, for 2 hours to break things, because they had better machines for breaking things than we had. And that was the entire link. But we also formed a view that engineers were different creative thinkers than architects, which fundamentally dispute. But the characterization, which kind of works, is that engineers are brilliant at solving problems, at drilling down to the answer. So this is characterized in the Ritter wicked problem sort of description as being a tame problem, where you go from the question, the problem that needs to be solved, to the eureka moment where you've solved it. It would ideally be in a straight path, but we know that there are going to be some false leads, but eventually you get there. Whereas the world of the architect is the wicked problem, and it's a beautiful way of being able to just say, chill, we can't give you the answer, we can give you lots of answers, and we will give criteria by which we might work out which might be the best answer. So, of course, for a wicked problem, you still start with a fundamental problem, and then you take it on this tortured path where new problems emerge, and you also have these blind alleys that we try and avoid in a tame problem solution, and we get to these eureka moments which were completely unexpected, options which may or may not be useful. There will be, of course, one option that we will decide at the end through the criteria that we've just discussed. This has been a great mechanism to be able to obfuscate the role of the designer, that we can argue that every designer has their own view of what design is, for instance, and that's why it's so difficult to define. That's why we have this wretched design thinking. I'll probably put my foot on it, but I am a great loather of the term design thinking, because it strikes me as something like music thinking or economics thinking or geography thinking. Design is design. If there's anything like design thinking, it's probably design. And just let designers have the flexibility to say what their take on that is. So from a very early stage, my career, I had at least 8 years of practice behind me before I became an academic. So the project as the seed for research had been in me from the beginning, because after all, that's what architects do. Every architectural project, whatever way we relate to it, is involving discovery, which is research. And this means that we have a particular take on what the role of students are in universities in something like architectural design. So this diagram is the encapsulation of the challenge for me, which has always been, what is the sweet spot where practice and the university and major research organizations can come together. And it's actually very easy to describe, hence this sort of facile Venn diagram. It's just at the convergence of the academy and practice and research organizations. Research organizations includes research departments in major industries, for instance. And the recipe is simple as well. In Australia, at least, for us to get going in this sweet spot, we just need indulgent clients who aren't in any particular hurry, governments who believe in tax-funded research for public good, practices willing to share their knowledge, universities able to work with real-world constraints, and postgraduate students willing to extend their architectural education by 3 to 4 years for a PhD. Every one of those is ideal, but to get that cake to bake, pretty hard. But we can make it easier for ourselves by looking at what others have told us. So the Boyer scholarship model is just brilliant for helping us all relax and understand that whether you're an undergraduate in the faculty or one of the eminent professors, you're all fighting in the same team and you're all looking at research. So design being research means that we argue successfully when we have to that an undergraduate is an essential part of our research effort. And in fact, at the moment, I'm leading an Australian Research Council funded project for looking at parametricism in place. Where do we get the qualities of place registered in a parametric engine? Quite hard. And we're doing that with undergraduates. And undergraduates were specified in the grant application as being the studio component of our research. And this was a very important award for us, apart from being a lot of money, because it means that those people who lurk around architecture schools saying that design isn't research were put in their place once and for all. Quite a lot of the schools in Australia would discourage people doing design research because it isn't real research. So my talk tonight is to assert the opposite. And the other thing, of course, it's hard enough to get faculties to talk to each other and do things, but it's just as hard actually within schools, across schools, doing the same things. This was an attempt to get funding from the European Council for Australian schools and for European schools. We succeeded. And part of this was just to show that design is pervasive across the whole of a university in some way. It may not be something which is their core activity, but it is something which will have relevance to them if they're able to find a route to apply their particular intelligence and knowledge to a design-based problem. And finally, I want to just talk about the transdisciplinary context, because we have had to argue, are we cross-disciplinary, are we interdisciplinary, are we transdisciplinary, multidisciplinary? Transdisciplinary is a great way to hide from all those esoteric debates, because there's a very simple formula. A transdisciplinary research project is only that because there is a project. It's project-based, not library-based. It involves at least 2 disciplines in an academy, and they have to be working on a real-world problem with an external party. And if you just use that as an umbrella, I find in Australia it's a very good way to dodge the bullets, because that is a fantastic way to do research. So without further ado, I will now go on to Gaudi and explain why he has been the model for a transdisciplinary research context and why his office that he created is actually a transdisciplinary research office. So just for anybody who's not been to Sagrada Familia, I better just get you into the groove. This is the building. It's spectacularly unfinished, but the level of unfinishedness is receding very fast. It will be completed in 2026 in time to celebrate the centenary of his death in 1926, age 74. He wasn't the first architect for the project. He was the second architect. He was a young, not very well off young architect, and I believe that would have been the reason why he accepted the commission to take somebody else's design forward. Now, the first architect was called Del Villar, and he resigned after a year, having got the crypt of the apse half constructed over disagreement on materials. So here's my first concrete reference. He insisted on not using concrete. Well, that's actually a little bit cute. He insisted on not using mamposteria, which is the Catalan for a kind of random rubble with mortar. So kind of, should we say, a kind of low-grade concrete as infill with ashlar masonry as the facing stone. So the original architect wanted to make it all in seated cellar stone, but and was asked by the client to reduce costs, said that's not the role of the architect to take instructions, technical instructions from the client, and handed the project back. And they then handed the project to Antoni Gaudi. Now, this is undoubtedly Gaudi's most important project, but it's arguable whether it's his best project. And so basically my talk is going to be a very fast track summary of the transition from an analog to a digital way of working, but also from Gaudi's design then and Gaudi's design today, because nobody working on the project would ever say that they are Gaudi's successors. We're simply the team that have been put in place to take instructions from Gaudi and make them viable. The technologies come in because of expectations that the project would meet the demands of being completed. And so rather than ignore the opportunities, these opportunities have been taken up. But it's led to a high level of innovation. Most of what I'll show you today it will be familiar in current projects, but I'll put a date to it and you can see that it's actually been a pioneering project over its life. The state at the moment is if you went to Barcelona today, you'd find that the main towers are almost the height of the existing towers. This is the facade that Gaudi almost saw completed in his lifetime. Two-thirds of the apse had been built. The crypt below it had been completed, so that was a consecrated space, and it has been operating as the parish church for well over 100 years. And the scaffolding had been removed from the first of the 4 towers on the Nativity facade when he, as I say, aged 74, was struck by a tram and died. He conceived the interior as being a forest, and for much of its life, the building has been visited as an incomplete space. There'll be people in this room, I'm sure, who've been there before it was finished, and that's what they remember. But in fact, it's now a completed interior. So 1926 is academic in a way, because nothing much is going to change on the interior, which was completed in 2010 and inaugurated by the Pope. Here you will see in a minute. So this is the big event. This is the real opening on November the 7th, 2010. And for once, for the first time, we could see the building as it was intended by Gaudi, a place of worship, a place of congregation. And then in the ensuing years, the glazing has been completed. And the idea is that the lower levels of glass, right up to 30 meters, are colored, whereas the upper levels of glass are clear. Now, Gaudi never wrote a word about his architecture or his theory. We've got hardly anything written by him. So all we have is the aphorisms that were faithfully recorded by his young assistants and some surviving documentation in the form of models. But we do have a clear understanding that Gaudi intended the upper levels to be clear glass. And when you see it, the effect of it is nothing short of magical. You go in there now, it's only been the last couple of years you get the full effect, but it means it doesn't matter whether it's afternoon or morning or summer or winter, or cloudy or sunny, it's always going to be different, and it changes while you stand in the space. It's absolutely awe-inspiring. There you can see this effect. It's a very difficult building to photograph. You can make great photographs, but no photographs will give you the effect of being there. So it's a good draw for anybody who's not been to go, and you won't be disappointed. But there are some very funny aspects about the use of technology. So I'm going to show you that it's probably, we haven't had anybody disagree, it's the first building to use 3D printing in any meaningful way. We were doing long-distance template production in the 1990s for stone production, despite the distance of 20,000 kilometers. We've been using video conferencing since the 1990s, again, way ahead of its time. And another novelty was, I think this would have been the first major building to have been scanned using a LiDAR. We got Australian Research Council funding for one of the first ever LiDAR scanners, which meant that we could, for once, actually model the existing part of the building that Gaudi produced, because we didn't have it digitally available until the last 10 years. So the space I'm going to describe the production of at the end is the Salic Relay, which is a huge auditorium sitting above the center of the building. And that was designed and largely built before we ever had a chance to see it in the context of the rest of the building. Obviously, we had drawings and sketches, but we couldn't have a 3D model. And the reason for that was, obviously, we didn't have the means to draw the existing part of the building. Every hour that's spent on the building has been about producing new parts of the building, not reproducing parts of already existing. So that's why we had to wait for the invention of the LiDAR scanner. But it also means that this is the last part of the building that I've been involved in. My contract finished in 2016 with the handing over the fully worked out schema, a spatial schema for the Glory facade. And with that effectively was the end of the design phase. And so all the work that's happening now is production, and it's in major overdrive. with an effort to get it finished. So what it looks like in terms of the task is shown in this video from the organization, the foundation. Sound seems to have... So this is finishing the building for 2026, and the first bit we're looking at is the sacristies. The first one was completed about 5 or 6 years ago. The Mary Tower will finish later this year, and then the cross will be next year. This has all been done now since the video, and that's the Salic Relay, the auditorium that I'll show you later. And then the 4 evangelist towers are now reaching on the outside. The Passion facade we worked on for 12 years, and that was completed last year. The baptistries are still somewhere out there. The Glory facade, as I say, the design schema was completed in 2016. The evangelist towers are now almost completed, and the main tower is well on its way and will be finished in 2022. So that's the story of the Sagrada Familia. And I'm going to, first of all, take you on a quick visit of Gaudi and why there's 2 phases to his career. There's Gaudi before 1914, when I argue he was a sculptor who acted as an architect. And from 1914, he was an architect with sculpture as his driver. And the reason I say that is because in 1914, he had 3 major setbacks. The first one was this building, which is the Casa Mila. It's an extraordinary story of innovation, but he himself was beset by the realities of the world, what Greg Lynn once described as contractor space. You can see here the plan for the building was very organic in nature, but if you actually see the as-built, you realize that even Gaudi had to straighten out his curves. These pieces of stone are extraordinary, but apparently took 4 efforts, each one, to get the stone to fit perfectly with its neighbor. But the perfection of the stone means we don't look at it deeply enough, in my view, because I think it's an extraordinary achievement, not least because it's actually a steel building with stone cladding, which is not a very well-known fact. Probably better known is that the building, when it finished, was so late and so much more expensive than expected that it was ridiculed by the press because it was no longer in fashion. Gaudi's type of architecture had disappeared. And also the client decided not to pay Gaudi his fee, which led to a big tussle in the courts. Gaudi won, got his fee, but it meant that he was being, as was the client, pilloried in the front pages of the national press for this. We'll skip Theo van Doesburg. Theo van Doesburg argues for 4-dimensional architecture in 1924, and Gaudi was actually well in pursuit of this. This is the Colonia Güell chapel crypt from 1896 to 1914. The first 8 years were spent building this fantastic analog computer. So the first architectural computer that I've been able to put my hands on was this model, which literally modeled the forces that the building was subjected to, gravity. The scale model is 1 to 10, so the weights are scaled at 1 to 10,000, which is appropriate if you work it out. And Gaudi then used tensometers to find out not only where the forces wanted to go with this particular loading, or any particular loading, but also what the forces were. And these discs are little cardboard markers where he records the tensile forces. So this is a fully equilibrated structure. The model itself was hanging upside down on site next to the project. He then turned it the other way around in a photograph, and photographed and then painted over the photograph. So after 8 years, this is what the client got in terms of, and it's quite, just think of a building or something in your life in 2011, which is 8 years ago, and imagine 8 years have gone past and you've been pretty much every week working on this project. And you've got as far as the painted over photograph and as well as the interior. On the other hand, you've just got yourself into a mood of a space of beyond the drawable architecture. So Gaudi's architecture is characterized for me as being undrawable. That's why I describe him as being a sculptor. But if you are an architect, you do have to represent the work quite fully if you want it to be built. And I think Gaudi reached his highest point with this building, and that's why I think it's his best building, because he actually tackled undrawable architecture, produced a three-dimensional, or you might argue four-dimensional drawing in the form of a model, which, being on site, was measured, and so the builders went ahead and produced this extraordinary space. I have never, ever turned down an opportunity to go and visit the building at least once a year. It just really does it for me. It's not a great reference point for concrete, because there is no concrete here whatsoever, nor is there any steel. It's entirely made from brick and from a basalt, which is found existing in these handy hexagonal prisms. But the building, nevertheless, was finished for its, it was, the crypt was finished in 6 years, but the building was abandoned. So that meant that it was a 14-year project, even more if you add, it depends on who you talk to, but the building can be visited as a crypt and it's consecrated, but it doesn't have the rest of it, and that's very unfortunate. It's a building which tries out a lot of new ideas, like using descriptive geometry directly in the form of hyperbolic paraboloids, as you can see here. There's a reason for this, and it's to do with addressing the fact that it's difficult to communicate warped surfaces to people trying to build it, even if you have got a string model hanging up next door. It's a building which uses the most modest materials possible. It's largely made from the ruined brick that gets overfired when you make bricks. Apparently, today it's different, but in those days when you made a batch of bricks, there'd always be a number that would get too hot and would distort. And Gaudi found a perfect building material. He used brick where he needed to along the lines of force, but elsewhere he just used this brick. And in terms of sustainability, these windows, he's adapted the knitting needles that came from the factory to which this church was associated. It was a so-called colony, a factory that was built outside of town with worker housing, and this little church was to meet the spiritual needs of the community. And even this grill was made from the cast-off needles from the process. So that's the quintessential Gaudi up to 1914, a real innovative thinker. He argued that innovation should come in design, not in construction. So this is probably a bit of wobble there for you. He felt that design was always going to be creative and innovative, but why would you invent a new material or technique if you had an old one that you could work from and work with? So that's why this was such an extraordinary space, because it's built entirely by brick and not by any of these new materials. Even more extraordinary because the client, Eusebio Guay, was the first person to produce Portland cement in Spain and was producing it for 20 years before he died. And Gaudi never, until the very end, took it up. And that's going to be a major point at the end. Why did he start using concrete? So having set this problem up, we then sort of think about what happened next. If he had these three buildings, the third one is Park Güell. That was also another disaster. I always ask people, what is Park Güell? And I'm not going to do it tonight because I've got to rush on, but I usually wait to get an answer, and it's usually, well, it's a park. And how many people in this room know that it's actually a failed gated community? Well, this is a very exceptional find. That's good. Well, that's what it is. It's a huge failure. If you were expecting, as the client was, 60 houses in this very protected environment, you were disappointed, because after all the years that were spent on it, The infrastructure was completed, but not the housing. So Gaudi had a lot of problems, and he's out of fashion. He'd taken a major client to court and won, so the bourgeoisie weren't particularly interested in using him. But worst of all, we had the Sagrada Familia under construction under his watch since 1883, spectacularly unfinished and probably unfinishable from most people's perspectives. What was he going to do about it? He got very ill with a disease called brucellosis and was convalescing in the Pyrenees. And while he was there, I imagine on his back, staring up in the ceiling, he would have been thinking about this very problem. And he realized that he'd have to take his sculptor's hat off and put his architect's hat on. These two gentlemen here, Senor Pucci Boada and Senor Bonet Gari, they were my first bosses in an architectural office ever. Reason for this is because in 1978, I visited Barcelona, having been exhorted by my university not to take Gaudi seriously because, quote, there was no school, meaning he might have been an interesting architect, but there's nothing about his work that we could possibly learn from other than perhaps these tragic mistakes. But of course, being from New Zealand, I argue that a red light is a green light for us, so to be told not to do something meant pretty much on the first plane. And I was astonished to go to the Sagrada Familia and find that it was still under construction. And because I'd imagined it was an abandoned ruin to the failed, sort of testament to the failed genius of Gaudi. And at that time, nobody in the Anglo-Saxon world was taking Spain particularly seriously because of the years and years of fascist dictatorship under Franco, who died in 1975. So you'll find that there's relatively little written about Spanish architecture during those dictator years, which meant as I'm assuming that's why I was given access to these two gentlemen who are both the directors, and they're almost 90, and they were the directors for the continuing work of the Sagrada Familia, and I found myself interviewing them for a thesis. I had no Spanish or Catalan, and they didn't have English. So it was in schoolboy French from my point of view. But in that interview, I had two questions for them, which was, where was the authority coming from to continue the building if, as we all understood, everything had been burned in the fire of Gaudi's studio in 1936, the first year of the Civil War. And anyway, even if they had authority, wherever that might have come from, how were they translating it? How do you actually explain to a builder when they turn up with their tools in the morning, here's this piece of stone from the quarry and we want you to make it into this shape because it's going here? And they told me that the answer was the same for both. It was the models. Because Gaudi had modeled the building, the main parts of the building at 1 to 10 and at 1 to 25 in plaster of Paris, and that these models had survived as fragments from the Civil War, and that the time that I was asking these questions in 1978 was exactly the time that they were initiating the broad sweep of investigation required to take the building from having just repeated the second set of towers to the main space. And would I like to join their office as an intern? Naturally, I said I wouldn't, because I was keen to get on with my next stage of my career, which is the so-called year between the architectural degree and diploma, where all of us wanted to go and work for the great late modern architects of the age, because we had had a very strong modernist education, and Gaudi didn't really appeal. But of course, once I got back to Britain and looked at the horror of what they were asking me to do, be going to do toilet schedules for Eric Lyons or somebody, I immediately wrote back and said I'd reconsidered, and of course I've never regretted that decision. By models, this is what a 1 to 25 model looks like. This is partly original and partly restored from Gaudi's studio. And it turns out these models are extraordinary because they're entirely composed of second order doubly ruled surfaces. Now, doubly ruled surface is a surface which has straight lines of which at least two will go through any point on the surface and lie on the surface. So this is a hyperboloid of revolution of one sheet. And you can see it's a piece of model fragment. And this is what I was shown and invited to come and join the office and unpack. So we find that Gaudi had studied descriptive geometry like all his students. The textbook he would have studied from in French. 1/6 of the course of an architecture program in his time was on descriptive geometry. And in that book, you can find this image of the Hyperboloid of Revolution of one sheet. Now, most architects in that course would have flicked through these pages, and I doubt they would have even noticed this, but Gaudi did notice it. And of course, it's very important because it gives a clue to how you might produce complex curved surfaces with reasonable facility if you're able to describe them with two straight lines. It turns out there's only 3 doubly ruled surfaces in the lexicon of that particular geometry. This is one. The other one is the hyperbolic paraboloid, which I'm sure you're all familiar with. And the third one is a plane. And the only difference between the hyperbolic paraboloid, the plane, and the hyperboloid of revolution is the plane has an infinite number of straight lines lying on the surface going for any particular point, whereas the other two only have 2. But that's very important. That's what a hyperboloid of revolution looks like in a mathematical model. I don't know if it's still the case, but if you went to the descriptive geometry department in the University of Barcelona School of Architecture, or in Hungary, and Budapest, another great seat of geometry and architecture, you'd find cases and cabinets, cases full of these models. I got this from the mathematics department at the university I was working at, and I've never been able to source the original of this, which is, believe it or not, a parametric analog model of a hyperboloid of revolution of one sheet. You can't see the hyperboloid there, probably, because all you can see represented by the strings are a cylinder and two cones, which are horizontally opposed. But if you twist that round, the yellow lines become the cones and the red lines become the cylinder. So I've actually got a digital representation of this to make it a little bit easier to see where we're coming from. So that is a cylinder that's been represented by 2 circles and lines which are corresponding A to A dash. And if we take one of those circles and lock it and move the other circle beneath it, it's like watching paint dry, sorry. Here we are, see if we can get this. See the emergence of the hyperboloid of revolution, and ultimately if you go around a full 180 degrees, it'll go to this point and no further. Now, this is fascinating because I don't know whether Gaudi saw the parametric model, but it means that we can see how he was thinking. He was thinking about sculpting still, so he's sculpting the hyperboloid of revolution out of that solid. If you take the cylinder, take it from the solid, you've got a sort of semicircular apse, and there is the work. And in terms of how he applied this, looking at the Clerestory Window, which is this window up here, the design for that was 1992 to 1995, but I'd already worked on the precursor, which is the lower lateral nave window in 1979 when I joined the office. This is the Clerestory Window. That is a photograph that was published before Gaudi died, so we know the window did exist. There's no fake news there. And here is the surviving technique that the model makers used to make his architecture. The hyperboloid of revolution is represented as half a hyperbola, which is, there's an invisible hyperbola there. That is half it in the zinc. And it's rotating around this plaster of Paris. It takes half an hour maximum, and you've got what you don't want, which is the master, in order to make what you do want, which is the half hyperboloid of revolution, and you then fit them together. So when I arrived, I had a week to show that, first of all, I understood what the problem was, which was to extract the geometry from these surviving fragments of model, and secondly, to have a strategy for working with the geometry. And on the end of the 3rd day, I went home, assuming that my probational week would end in tears, because I simply did not have a clue. I did appreciate that they were trying to get these surfaces to intersect with each other, and I did appreciate that the intersections between each pair of surfaces would end up being a point known as a triple point. But it wasn't until I came to work the following morning that I'd realized overnight I'd been visited by something. There was no vision, no dream, but in the morning I knew I'd seen this problem before, and that is, it's in nature. That is the shape of all mountains are triple points. And I always say, look out the window at mountains next time and you'll find there are always going to be intersections between two adjacent surfaces, and the intersections will always come into a triple point. Obviously you can have more, but if nature's working towards the minimum, then you are going to get only 3 surfaces, and each peak is always going to have 3 crests running to it. So that meant that I could take these models, measure them, find the triple points, which that's me doing that. And in this environment, I've got to say that the office I joined, I was the only full-time architect. The two, that's Senor Bonnet Galle and his colleague Puchibara, they came in for 2 hours every day. I thought it was remarkable that people in their 90s, well, just turned 90, felt that that was the best use of their time, but thank goodness they did. We were the architectural team. There were 4 draftspeople, a sculptor from Japan, Tsuro Soto, who's still there now, a clerk of works, and 1.5 administration people, and 40 stonemasons. And they were looking forward to having the building completed in 10 years. I wasn't quite so sure, but I was young, and the force of optimism has remained with me since. So I'd like to pass that on. So I realized by the fact that this was a piece of geography that we could actually map these surfaces, and that's what these are. These are contour maps of equidistant planes taken from a notional center of the window, and that is how we worked before the age of the computer came. And you can see that the line work was everything. For many years I was cast as this digital dude, which really irritated me because I was actually a draftsperson. I like drawing by hand, I miss it, but I'll be the first to say that it actually doesn't have prospects if you're trying to get things done in reasonable speed anymore. The drawings are absolutely festooned in little calculations. So nothing that I'd been taught at school had prepared me for this. I hadn't been taught how to measure models. I hadn't been taught how to extract geometry. And I certainly had no expectation of using mathematics. But in fact, everything had to be calculated. We had to invent a way to communicate this information. So there is the half hyperbola, which is the section through the rotated hyperboloid that goes to the stonemasons. It's coded with a letter. This is Hyperboloid J. There you can see it's 1980. And here you can see the representation of where these hyperboloids would go. So this is as close as we ever got to drawing the building. We were just literally giving diagrams to the model makers. When it came to the computer, the simple fact is we're trying to get each of these surfaces to intersect so that we can get a digital model that's equal to the surviving fragments. And for those who are parametrically interested, there are 9 variables for each one of these surfaces. There's its position in space with 3 coordinates, its rotation about each of the axes, so there's 3 axes, and then there's the surface itself. There's an A, which is the dimension of the collar on the X axis, and there's B, which is the distance on the Y axis. If A equals B, it's circular. If it's not, it's elliptical. And there's C, which is the degree of separation between the 2 generating circles that I showed you earlier. So there's 9 variables that will influence the way that these surfaces will come together. So when you look at this video, you're seeing, there's the triple point. Just a subtle variation of the rotation of one of these surfaces and the other surface is enough to produce such a massive effect of change. Now, obviously, if you start moving, and that's only a few degrees of movement. So I'm just showing you, this is, if you just follow that curve there, you're seeing the elliptical surface just rotating by a few degrees, and you're having this effect. So it's great that we can digitally resolve this, but it's extraordinary that Gaudi, of all people, was able to do all this in his head. So that's my major point there. In terms of applying this, you can look at the the entire surfaces of the nave interior, as I said before, are made from these doubly ruled surfaces, but the Hyperboloid of Revolution is the predominant surface. And the hyperbolic paraboloids are used as sort of decorative interfaces. So all the work for the design work for the nave was undertaken in the period of 1979 to 1999. And although we were using parametric design software from the aeronautical industry from 1991, unfortunately, the digital fabrication aspects were way, way in the future. We were actually using robots on the project in terms of robot cutting before we ever used a computer. So in 1989, there was a CNC-driven saw that would help us with the columns. But in terms of anything else, it was actually, we were out in the wilderness. So when we started making the Sagrada Familia Hyperboloids of Revolution, they're generally made from what we call artificial stone, but concrete manufacturers would love to call concrete, because that's what it is effectively. It's 5 different aggregates and 3 different types of cement to get as close a match to the sandstone, which is the Montjuic sandstone, which is no longer available because it comes from a national park just outside the center of Barcelona, and quarrying is not permitted. And it's taken until recent years to find a source of any stone that's anything like it. And I think actually the moment we're using a granite, which is not sandstone, but has the color variation of the Montjuic. So starting by extrapolating Gaudi's own design process to 1-to-1, you can see that the Hyperboloid of Revolution has been made using the half hyperbola, rotated, and this has been made into the master, from which the things we actually want are being made with plaster of Paris and Hessian. So a very hands-on process, despite the fact that we were using parametric design software 15, 20 years ahead of everybody else. So I think it's one of those wonderful things about life, that there are these ironies and paradoxes. So it's a very messy process, but nevertheless it's a very precise process. We're talking about millimeter accuracy, not centimeters. And these pieces are being put together in the Gaudi way to make the master for a glass fiber reinforced mold, which has been used for the in situ vaults. So there you can see it in production, and here you can see it in use. So this is a mold from the 1990s that's been made from that extrapolation of Gaudi's technique. And then you can start seeing the real logic appear. Why was Gaudi using these doubly ruled surfaces? I've obviously pointed out that they were a tremendous benefit for being able to describe the task so it could be built, but they also have a logic to them. So if you're going to put reinforcement, there's the hyperbolic paraboloid in the background. It's the best possible reinforcement because all the reinforcement is in straight lines, no curves required. And also Gaudi described these surfaces as surfaces which light would glide over. So he really understood the aesthetic of them. So that is the artificial stone vaults, but effectively concrete. And they've been bush hammered now and it looked like artificial stone, but that was how they were made. They were concrete put into these molds. And that has allowed the project to advance very quickly. On the other hand, there are other parts of the building which, for various reasons, even though they're structurally made from concrete, surface are made from the Catalan vaulting or Catalan tiling. And again, you can see another reason for these straight lines being just a perfect way for the production. This is the former for the hyperboloid ceilings, and it couldn't be simpler, just hoops made from angle iron and a sufficient number of these straight lines to give the form so that the tiles can be laid against them and this removed and reused. So that's why Gaudi used these surfaces. That is why the building has been able to be completed at the speed that it has. And it's also why, despite the fact you'll read copious opposition to the project continuing, I've seen it being described as a disaster. It's being that Gaudi's design is being messed about by mediocre technicians. But I would argue that, I won't argue about not being mediocre technicians, but I will argue strongly that Gaudi was extraordinary in the sense of the future and putting an architecture and geometry relationship together to make this a viable project. Now, I see it's 7:05, and you'd like me to finish at 15:15, maybe? Yeah, 10 minutes? So I'll just now take you through the application of the geometry in today's context. So that was then, and I'm now going to show you what happens when you migrate into digital fabrication by looking at the two projects very quickly. First of all, the Passion facade. This is the design team. So it's a proposal by Gaudi, and then the two senior architects that were my first bosses had spent 17 years working on it. The design team is Geordie Bonnet, who's the son of this Geordie Bonnet, but has been the director for years and years and years until about 7 years ago, I believe, and my partner Jane, and then that's the documentation. So we had this already. So this is the pre-digital interpretation of Gaudi's drawing for the Passion facade. So when Robert Hughes laid into the building in his massive work called Barcelona, it's 700 pages, I think he did about 40 pages demolishing Subirach's work for the lower part. I don't think he had any idea that that was only the bottom half and there's this top half. And this photograph is the only surviving evidence we have of Gaudi's intentions, not even the drawing, just the photograph. But I've argued that this is a 2.5D representation, that we know that he's described this as being a facade that should be seen at closing day. It's facing the setting sun. It's about the crucifixion of Gaudi, whereas the nativity facade is about the birth of Gaudi, birth of Jesus, sorry. And that's jet lag in action, all right? Some indulgence. The nativity facade is facing east, and it represents the birth of Christ and is a very hopeful and optimistic facade. The Passion facade represents the passion of Christ, and it is meant to represent the pain that Christ suffered for all mankind, humankind. And this, therefore, is open to interpretation. From an artistic point of view, Subirach took Jesus and the cross from down here and put it up here, but we felt there was little license we could do other than to say, what would Gaudi do with this drawing had he been in a position to apply his doubly ruled surfaces to it? And we saw these as bones, and this is the original model that was produced pre-digitally. And it's a testament of what happens when you try and use these surfaces without computation. It's impossible. If you want to use these surfaces with elegance and without the clunkiness, then you need to compute. We still start with a drawing. This is my sketch for an idea of perhaps we could combine these doubly ruled surfaces such that there's only straight lines for intersections. So the Hyperboloid of Revolution here is intersecting with the hyperbolic paraboloid along a straight line. And this is a design problem because P1, P2, and P3 are points in space that we want to, we don't want them to end up there. We want to say where they are. It's a design. So we're trying to get this mess of parameters to work. And that's why we went straight to a mathematician rather than any other shortcut, who wrote the various formulae that went to produce this. So 8 hyperbolic paraboloids and 1 hyperboloid of revolution intersecting with that degree of elegance. This is the only drawing for the project, which is the schema that came from the mathematician that explained the problems and the parameters. This is 2003, this work. And this is the Rhino model. We were scripting in Rhino before Rhino had scripting interface, so we have a close relationship with Bob Mcneal, and we're able to look at adapting affordable software. So the elephant in the room for many years was I would show the parametric design in the 1990s using this engineering software, And I would write, in 5 years' time, I wrote in 1992, we'll all be working like this. Trouble was the software was, in today's money, was $1 million, and in today's money, the computer was $500,000. It was, in those days, it was $250,000 US for software to do planes and the Sagrada Familia. So it was a very important stepping point for us in the early 2000s to be able to have something like Rhino, which would had the facility to do really deep level programming to make it work for us. And here you can see the first application of a 3D printing in an architectural project. This is, sorry, the second. We'd already used it 2 years earlier with the wax Firmajet. And here's the model itself. This is Jane's work. It's a parametric model. The image you see is the consequence of all these black lines of relationships. So the way you build this architecture is either using an Excel spreadsheet or tinkering with the formulae. You don't actually move lines around with the mouse. You design the lines to be where they need to be. And there is the parametric model. It has not a single dimension on here which you can change without it having a knock-on effect, a cascading effect elsewhere. So it's from our point of view, we would ask ourselves the question, if Gaudi had the computer, not what would he do that would be different from what he had done, but how would he do what he did differently, if you see what I mean. So in other words, extend his repertoire as far as you possibly could using these tools. So if you had parametric software that would allow you to relate every single dimension, then surely that's what you need to do to get the fluency of his architecture. We had, as I said before, we didn't have a 3D print of the building, so everything had to be done on this without ever being able to relate it to the rest of the building. One thing we were encouraged to do was to make sure that the ellipse of the rose window that we'd built in the previous decade was fully visible from the footpath and not occluded in any way by the columns. We built prototypes using a boat builder and 3D cutting in the early 2000s, and that's what it looks like. That's polystyrene, and the reason for this was so that we could put them in place and gauge whether they were any good. So this is like one-to-one prototyping. And even the hexagons on the top were programmed to be parametrically variable so that we could shift them around, and we could then start comparing the prototypes with the Gaudi's original drawing. The production of these has been a fascinating story. So another innovation that I would encourage all young architects to take away with them is see if you can get yourself into a situation where as you design, you speak to the person who's going to be building it. Because that is one of the fundamental differences, and that is why the Sagrada Familia is a living laboratory. Nothing was ever done in the drawing office and then handed over to a builder and say, now build it. It was always negotiated. What's possible? In this case, Jordi Barbagne, who's the third generation stonemason, is explaining to me why these, just because we can make them impossibly thin with the wax 3D printer, would get damaged. Even if he could make them, they would get damaged in the building because each one piece weighs several tons. So we would work together on ways of production. In this case, we were looking at whether a diamond wire would be able to cut the shape. And we were looking at textures, and we were looking at how to do this as cheaply as possible. So part of our work was to design the piece of stone that would need to be extracted from the stonemasons in France, cut to shape, and then as little as possible given to the robot to work with. So there you can see the blank. That's been cut to order from the quarry. This has been shaped to being as close as possible to the robot. And then Jordi Barbagne himself had programmed the robot with a 5-axis robot with a 2-axis turntable to give a 7-axis solution. And so the columns were produced 6.5 meters long, absolute fraction of a millimeter accuracy. Only temperature would make it out. Still need to have a degree of handcraft. Still need to produce a 1 to 10 model for being able to explain day to day. So none of the old things are thrown out. It's just that you augment them with all this new technology. And there you can see the column in place. And then the last bit to talk about on this is the story of its construction. The building team, also part of the team, so it's not contracted out, was so confident in the process that they decided to start from the edges and work on the way in. And as architects, we're saying, don't you think you should start at the beginning, in the middle, and you can accommodate any error at the edge? And they refused to do that, with good reasons, it turned out. I can't remember what the logic of starting that way. I think it was to get the team on one side working, and then they could do the other side. The reason this is the world's most complicated project, by the way, is not only is it as complex as any piece of architecture to construct, it has the additional challenge of 4 million visitors going in it while it's being built over them. So you can imagine what logistical. And you can see all this parametric precision has led to a building precision as well. And there you can see it beginning to encroach on the window there. And I'll just rush through the as-built. Which is somewhere here. So, and here's the two ends coming together, and you can see why there's no room for any error, because you can't just take a piece of stone and shave a centimetre off it very easily, and then you'd destroy the continuity of all these intersecting geometries. And finally, there's the sepulchre at the back of the facade. And there's this challenge from the director. And there you can see it fits perfectly. So in fact, while it's ideal to have a 3D representation to work from, it's not essential. And there it is, finished with the cross. And just one last tale, which is one of off-site fabrication. The unusual aspect of this project has been the for some reason my monitor's gone very small, that's why I'm struggling to find things. It's tiny little writing. Here we are. So digital fabrication, none of the work on site is made on site, it's all made off site. It has been for the last 12 years. The Sagrada Familia was always spotted as being, it was going to be the biggest religious building ever. So that's on target. Why did Gaudi not do anything as elaborate for the attic space as for the interior? This is an interesting question, but it led to quite a lot of debate in the office. One was, hey, this is just a service space, it doesn't matter. And the other was, oh, but all Gaudi's attics are amazing spaces, but obviously it's the last thing you design. Let's just get this published so that the donors can see what's coming from. Here's what a Gaudi attic can look like. This is in Bella's Guard, and you can see he's even saving mass by using this herringbone pattern of this brickwork in the attic of the Casa Mila. And we've realized that something had to be special about the space. And it's the point where everybody collects before going up the main tower. So it was decided to make it into an auditorium. And for the first time ever, we worked across a 3D model as a team. This is in 2006. And we just assumed that architects everywhere were working in 3D models and teams, but in fact they weren't. So there was another little innovation. And originally the thought was to have the auditorium going right across the tower, but I realized that actually there was an opportunity to have it floating in space so that you could get light in above and in below it. And that's where it is in section. It's right over the altar, the crossing. So it's a very important space, but there is no precedent. There's no great Gothic cathedral that has a visitable space above it. In terms of Jonathan's comments at the beginning, we don't have any separation between architecture and structures. The structural team is part of the architecture team. That's Carlos Bouchardet. Never been any embarrassment in combining original fragments of Gaudi's model, handmade models, provisional materials, and machine-made models, or having digital projection down in the plaster model makers lab. I argue that the model makers workshop, in fact, is the real living laboratory aspect. If you visited and only had 5 minutes, that's where I would have taken you to, because it was where all the major decisions were made in this mode. And that's what the parametric model looks like. Each one of these is a spatial element that has its own team behind it. And with the invention of 3D printing, we were able to produce 1 to 100 versions of it in 1 week. When I asked the head model maker who'd been there for 49 years whether he was insulted by this kind of migration to the technology, he looked at me as if I was mad and asked me why I thought having his arms in a plaster bucket, in wet plaster all day was his idea of fun, when he could get these plaster of Paris pieces out of the machine and spend his days putting them together to make like a giant Lego. We were looking at ways to innovate because of the circular nature of the space. Gaudi was never able to use a curved surface because of the way he made his models. But we, with our digital fabrication, could start looking at curvature, which gives it a kind of more Baroque feel. And then you can see this in space. Now, what we couldn't do was calculate the lighting levels. And there was... if I'm asked for the definition of trust, this was it, because I was asked as the lead architect, would it be light enough in there? And so we're using Australia's best renderer, and you can see from the way he's got the detail on the metal and the glass that he's no slouch, but it's just impossible to visualize the unfamiliar, we found. Hardly any of these surfaces are flat, apart from the ones you walk on or sit on. And the texture, we just got no real understanding of whether it was going to be bright enough or not until the scaffolding came down. This is the last remnant of in situ concrete making before we moved over to fully digital off-site fabrication. You can see here the elements being applied. And these are precast artificial stone elements made off-site. And I've just got one last batch of, if I can find them. So a wonderful amalgam of in situ and precast. So Catalan vaulting going there, precast elements here, and the bit that's already built has been built in situ. So the take-home here is that you can combine new materials and old materials, new techniques with traditional techniques, and get away with it. Here you can see the off-site fabricated shuttering made of plate steel for these very large in situ elements. And by working parametrically, we were able to use optimization to make sure that no part of the thickness is greater than 15 centimeters, which is just a wonderful thing to be able to do, to know that you really are making this as light as it possibly can be. And that gives you a sense of the size of the space. A lot of reinforcement for the in situ. And then this picture here, which is stone on the outside because it's deemed as a 1,000-year design life. We do know that stone will do that. And it's more economic to make artificial stone on the interior. So that's why you get this. When I have had visitors at this point, I'd ask them which was the stone and which was the artificial stone, and nobody could see it unless they're about a meter away from it. It's an incredibly successful technique. And just a final few pictures of it built. So the scaffolding came out, and it turns out it's plenty bright enough. And I'll leave it there. So you're looking at a lot of concrete and a lot of history, and thank you very much for your indulgence.